A ball of mass 4 kilograms rolls up a slope at an angle of 25 degrees to the horizontal. The coefficient of friction is 0.3. Given the initial speed of 9 meters per second, find the distance the ball travels up the slope until it comes to rest. Okay, so I'm going to draw a picture of this, like so. We have a ball going up the slope, or a ramp, and I'm going to make some assumptions here. So first I'm going to assume that this ball is a sphere, which is fairly standard for balls. I'm also going to assume that when it's rolling up the slope, it's perfectly rolling, or rolling without slipping. So if you think about it, so you have like a, that's a terrible ramp. If you have a block and it slides down the like a ramp without friction, it will have a different speed at the end, like a lateral linear speed, than if you have a ball which rolls. And that's because some of the kinetic energy is converted to rotational energy when you roll, and when you slide, all that energy goes to translational. So what I'm going to assume here is that this ball is perfectly rolling without slipping. So slipping would be like the block, rolling would be like the ball. Now, those are the two extremes. You can kind of do a little bit of each. So what that would depend on is basically, I think, the coefficient of friction going into it. Now, another caveat is that when a ball is rolling without slipping, then the point that's actually in contact with the ground isn't moving. Is that part of the ball isn't moving with respect to the ground. And what that means then is the coefficient of friction that you use is the static coefficient of friction as opposed to the kinetic. Kinetic would be for sliding, and static would be for rolling. So I'm going to assume that when they talk about the coefficient of friction here, and they're generally different for materials, that they're talking about the static coefficient of friction because it's rolling without slipping. So those caveats mentioned, I'm going to solve this through conservation of energy. So I'm going to say energy potential initial plus energy kinetic initial will equal energy potential final plus energy kinetic final. Now we're assuming that, I'm going to assume that the zero potential energy is at the bottom. So it's going to start with zero potential energy. It's going to have some kinetic energy. And then at the end, when it's stopped, I'm going to assume that since it's rolling without slipping, the stopping of the rolling happens at the same time that the translational motion stops as well. So I'm going to assume that energy kinetic final will be 0. So I'm going to rewrite these, and I'm going to expand this energy kinetic into the translational 1/2 mv squared plus 1/2 I omega squared, where this is the moment of inertia, which is I, and omega is the angular velocity. So then for potential energy, we have mass times gravity times height. Okay? So this is the translational motion part. This is the rolling energy associated with it. So now we want to do is we want to find out what this I is and omega is. So I, that's going to be dependent on the geometry of the ball, which we assumed was a sphere. So we come here to list of moments of inertia, and we have a ball, a solid sphere. Oh, it even says it's a ball. Convenient. 2/5 mr squared. Okay, so we go back to the problem. And now we have I equals 2/5 mr squared. So now we need to find what omega is, angular speed. So x equals theta r. V equals omega r. And acceleration equals alpha r. This is the conversion between linear and angular velocities, or I guess distance, velocity, and acceleration. So the way I remember this is I start with this, because if you think of a circle, the distance around a circle is 2 pi r. And if you think of that in angular terms, well, the angle around a circle is 2 pi, and when you multiply that r, you get the same answer. And so this is the kind of form you're going to have. You're going to have the linear on the left, and you're going to have the angular on the right, multiplied by the radius r. So we look at this portion right here. Omega equals b over r. Omega squared equals v squared over r squared. And we plug that into the equation that we have up here, and we get light blue, 1/2 mv squared plus 1/2 times 2/5 mr squared times v squared over r squared equals mgh. Okay? Do some canceling and combining here. And darker color, dark purple. So the masses all cancel. That is interesting. Okay. So the mass is irrelevant? Maybe. I don't know. I guess you could probably use the mass to determine if it is perfectly sliding or not. Or perfectly rolling versus if there's sliding involved. Not quite sure. Okay. Focus. So then we have, let's see here. I'm going to multiply this by 5 over 5. And so we have 5/10 v squared plus 2/10 r v squared equals gh equals, combining these, we have 7/10. Yes, we do. 7/10 v squared equals gh. Rearranging everything to find h, we have h equals 7v squared over 10g, which is that right? That feels funny. 1/2 mv squared, 2/5 mr squared. Yeah, maybe. Yeah. Yep. Seems reasonable enough. Okay. Which is 7 times, our initial velocity was 9 times 10, and then I'm just going to round off gravity to 10 to keep things simple in life. So we have 7 times 81 divided by 100. Go to our calculator, on, clear. 7 times 81 divided by 100, and that gives us 5.67, which is respectable meters. So we take 5.67, that's going to be this height right here. And then, so we know we'll do SOHCAHTOA. We're going to use the SO. So we know that sine of theta, which we know is 25 degrees, equals opposite over hypotenuse, which means that hypotenuse equals opposite over sine of theta, which in this case is going to be, I'll call this x. X is 5.67 over sine of 25. Yeah, seems okay. Maybe let's do this. So make sure we're in degrees. We are in degrees. We'll do 5.67. Good. Divide by sine of 25. And that gives us 13.41. 13.41 meters, which is a pretty good roll. Now I'll find the distance the ball travels up the slope until it comes to a rest. Okay. So the distance the ball would roll would be 13.41. So a couple things to think about real quick. So the energy that the ball has initially comes from both the translational, basically moving side to side energy, but also the energy stored up in the fact that it's rolling. It's angular momentum. Coefficient of friction, given the speed, find the distance the ball travels up the slope until it comes to rest. Okay. So that's how far it'll travel. Show that after coming to rest, the ball will start rolling back down the slope. Okay, so the way I would look at this is I would draw a picture. So here's a slope. Here's the ball. And so we're going to have so we have, let's see here. This will be force of gravity. This will be force gravity, and I'm going to call it the x direction. This will be the x direction. And, gosh. Show that after coming to rest, the ball will start rolling back down the slope. So we're going to have a force of friction as well. So the forces acting on this will be force, friction, force, gravity. And since we have two forces that oppose each other, there'll be a torque. And since they're not lined up, there's a distance between them. That's going to cause this to roll, since the force of friction is at the bottom of the ball, but the force of gravity can be assumed to be at the center. And since they're not lined up, it'll cause a torque, which will cause the ball to roll. And I don't know how deep of discussion they're looking for there, but for me, this picture would convince me. Like, oh yeah, this picture's great. I guess that depends more on the grader. So find the speed of the ball when it returns to the starting point. Okay, so my assumption here is there is not going to be any energy lost due to friction, because the friction is causing the ball to roll. If the ball was sliding, then we'd be losing energy on the way up and the way down due to friction. But it's not. The friction is causing the ball to roll, so that energy isn't lost. It's just converted into rotational energy. So the speed of the ball when it returns to its starting point is going to be the same as its initial speed going up. So I would say that for C, when the ball gets to the bottom, that will be 9 meters per second. So same as we started, conservation of energy. And that is how I would approach this problem. Hope that helped a little. I will see you next time.